Welcome back, everybody. This is session 6 of the developer training for HiPAS Gridlab-D. And the topic for this week's session is the core engine and solvers for the various modules. Before we get into that, let's look at the homework assignment from session 5. If you recall, the assignment was to record the indoor air temperature and energy use for a house in Washington State, and plot the energy use. And so there were a couple of hints to help you get this done. Since there's no weather data for the city of Pasco in Washington State, the nearest weather data is for a city called Yakima, which is probably about 60 miles to the west of Pasco, but roughly the same climate. Another hint that I provided was that because of initialization transients, which is something that we talked about previously, it's a good idea to start the recording later than the start of the simulation itself. So if we want to start the recording and collect data on January 27th, it's a good idea to start the simulation a few days earlier, and then use the in-service property of the recorder to enable the recording on the day that we actually want to record. And of course, the stop time of the simulation will be set to the end of the day, and so we don't really need to put in an out-of-service property since there's no sense in continuing the simulation after we've collected all the data that we want. Another important hint was the transfer function that's used to calculate a finite difference. When you look at the energy use in the house panel, it's an accumulated energy use. So what you see is the total energy use growing over time. And so if you want to collect the energy use for an hour interval, you have to set up a finite difference transfer function. And the definition of that transfer function is provided in this hint. There are various transfer functions, and over time you kind of learn which ones do this, but you can look this up at Wikipedia as well. These are sort of standard definitions for various commonly used transfer functions, integrators, delays, and then this one, difference, which is z minus 1 over z. And that definition with the time step of 3600 seconds gives you a 1 hour time difference. Finite difference for calculating the energy. So if the input is the total energy accumulated over time, then the output will be the time difference energy. So it would be the hourly energy use average for that hour for each hour in the simulation. So let's look at the solution. In this case, what we've done is the first thing is we've set the clock. And notice that the clock starts about 1 week before the simulation itself is needed to start. So the data collection starts on the 27th, but the simulation starts a week earlier. This deals with the simulation transient that might occur as a result of setting up the simulation. Since we're looking at one house, it's probably not going to need to be a full week, but I'm just in the habit of making these a week. It's sort of a safe interval. By the time a week has elapsed, all of the potential errors that might accrue from incorrect initial values would be gone. They would be dissipated and no longer part of a simulation output, and so you wouldn't be so worried about having those kinds of errors creep into the results. The next thing is just specifying the weather, and so in this case we use the input macro, and we provide the weather file, and that converts the weather file into the object necessary to incorporate it into the simulation. We specify the residential module, and in this particular case, we're specifying a couple of gas end uses. That's really pretty typical for that area, there be only certain gas end uses. In this case, we just put the dryer and the heater. You could, of course, have all electric, which is not at all uncommon in Washington State. Or you could have, other end uses such as cooking or water heating as well. So that's just something that is a modeler's discretion. I just chose to use that in this case. Next thing is to specify the CSV header type, because we're going to be loading these CSV files with the plotting tool. We need to use sort of the standard header type that Pandas wants. And so that's what specifying just the name header type. It makes the CSV file only have the field names and no other comments or anything. Next, we're going to create a usage property of a house, which is the thing that we're actually going to be interested in looking at. So we're just making it a double. We could put units on it. It doesn't really matter. I didn't bother in this case, but you could very well put the units of kWh per hour. And then we define that filter that we talked about. And we define a house, and we connect the panel energy use to this usage parameter that we created using the difference transfer function. So that allows us to get the hourly difference in the total energy used by the house. And then finally, we put a recorder in to record the air temperature and the usage that we've defined here into a file called house.csv. We sample this hourly, and we start the recorder on January 27th, 1997. And at this point, we've basically done everything we need to collect the data. And finally, when the simulation ends at the midnight on the 28th, we just generate the plot. And so in this case, we're plotting the input file is this recording that we have from the CSV. This just specifies that it should rotate the labels 90 degrees. As you can see, the x-axis labels are rotated. And then we set the title. So this is just things related to the decoration. We use the time step from the CSV file on the x-axis, the usage on the y-axis. We ask it to put a grid. And this tight layout just eliminates a lot of the white space that you get around the plot. Often when you generate these plots, we really want just the plot and no extra space around it, because we put them into reports and things like that. This avoids you having to clip or do any kind of cleanup afterwards. And so as you can see, the result is something fairly typical for a winter energy use. There's more energy use at night with the heating related things, and then there's less energy use during the day. So you see some lighting load and other things that are related, but generally this gives you a sense of what we're getting from a system like this. So this is a pretty common way of doing things in Gridlab-D. It sort of covers all the bases. There's a lot of different things that you could turn on and off here and try out and see different results in the simulation. Okay, so today's session, we're going to talk about how the solvers in Gridlab-D work. And there are three principal solvers used in the simulator. There's the core solver, which deals with the overall simulation itself. It's the solver that's responsible for advancing the clock and dispatching the other solvers that would be implemented in different modules. And so this core solver is running through the loop of each object, updating each object as the time advances. And so it's solving these objects for their steady state. And then once it solves the steady state of every object, it uses the object's time step to figure out what the time step for the whole simulation is, and advances the clock, and then redoes the process over and over until every object states that it is essentially running in steady state and no longer needs to advance the clock. The core solver can be run parallelized, so we can actually solve multiple individual solvers simultaneously where that's possible. That, of course, requires a multi-threaded system. But generally, it's not necessary to use this granular level of parallelization. And for certain solvers, it actually doesn't really work quite the way you might expect. And so as a general rule, people don't use the multi-threaded solver internally. Instead, what they do is they run Monte Carlo simulations and lots of solutions, and individual solutions, the time that they take doesn't really matter. What matters is how long it takes to, to run a large batch job. And so parallelization across many simulations is more effective than parallelization across the objects within one simulation. So as a general rule, we don't use that very much. We'll talk then about thermal solvers and how we solve the dynamics of buildings and how temperature changes in the building as a function of energy inputs and heat gains and losses from the ambient environment, occupancy, etc. There are actually two types of solvers implemented in Gridlab-D's residential module in particular, the 2-zone, which is used for small buildings, and the 4-zone solver, which is used for large buildings. And we'll talk about how both of these work. And then we'll talk about power flow solvers, which is really the crux of what Gridlab-D does. And there's a lot going on in the power flow solvers. We'll talk about how the individual components work and how the various solver methods that are available differ and how you use them. So let's get right into it. Let's start with the core solver itself and how the system works, the overall methodology that's used for solving in Gridlab-D over time. So if you recall, we've talked about this before, there are several steps involved in the simulation at a high level. Initially, we start by creating objects. And then once all the objects are created, we initialize them. And then we begin the main time loop, which we call the sync loop. And there's actually a variety of steps involved in doing that synchronization loop. And we'll go over those in some detail. And then for each loop, we check whether we reach an iteration limit for that time synchronization. And if we reach that limit, then the simulator stops. That limit is by default set to 100. It is rare that you run into problems with that limit, and generally if you do, it's because one of the objects isn't working correctly. It's not at all common to find that the main iteration limit is what's reached. What we often find is that the internal solver limits, the power flow solver being the most common, reaches its iteration limit. But the main outer loop solver, it's very unusual to have to do anything with the iteration limit on that one. And then finally, if the time step synchronization is told that all the objects have reached steady state, then there's really no time to advance to anyway, and that would also cause the main time synchronization loop to exit. There are other ways that the main loop can exit. Think of these more as sort of error, exception handling. If any of the objects returns an invalid time step, that causes the main loop to exit as well. If there's a synchronization timeout, so there's a maximum time that any object is allowed to run its synchronization event, and that's controlled by a global variable called maximum sync time. The default, I believe, is 60 seconds, which is a very long time for a single object to synchronize. But as it happens, there are some solvers which actually do need that much time to solve. In particular, Newton-Raphson swing buses, I believe, may need that much time to solve the Newton-Raphson problem. And then any error message which is generated while the global ignore errors is set to false would also cause an exit of the main loop. And of course, any exceptions raised in C++ or Python code would cause the main loop to exit as well. These would each be associated with some kind of an error message. Typically, the first type, the invalid timestamp, results in an error message saying that an object returned an invalid timestamp. This one results in a SIG alarm, which I believe is an exception 14, an exit code 14 from the simulator. And then this one just results in an exit code of, the simulation failed with the error message. And this results in an exception exit code, all of which can be identified with an on-exit macro. Okay, so that's the main level. Now, what we can do during object initialization is interesting. So first of all, every object is given an opportunity to initialize. The order in which they're initialized is basically the order in which they're created. And if that initialization succeeds, the handler returns 1. And of course, it returns 0 on failure. However, an object can defer initialization if, for example, it needs another object that it has some relationship to be initialized. It can return a status of 2, which basically means call me again later. It will actually call them in the same order, but only the ones that have deferred initialization. So this allows an object to wait until another object that comes later has finished its initialization, and then it can complete its own initialization. And so this deferral loop will continue until all the deferred objects return 1. Of course, they might return 0, in which case everything would fail. But what it tries to do is get all the objects to return 1. There is a limit on how many retries there will be in initialization, and that's set by the global init max defer. But again, unless you have sort of a deadlock situation where 2 objects are mutually waiting on each other, you should never encounter this this limit on the maximum deferred attempts. Okay, so once initialization is complete, then we go into the main synchronization update. And so I'm going to go into some detail on how this works. So let me first point out some details about how timestamps are handled, because a lot of what's going on within the synchronization updates is really about calculating the next timestamp that's used for the update. So first of all, timestamps are all defined in seconds from 1970 UTC midnight. Timestamps actually include nanoseconds, but we don't generally use them unless we're running in what's called delta mode. But in steady state mode, there's no need to look at nanoseconds, since steady states are calculated down to about down to a 1 second resolution. So anything that's sub-second would require delta mode anyway. So let's just skip that for now, because we're not going to talk about delta mode. Valid timestamps are basically the form that you see here, one of the ISO forms. An init value just means 0, which corresponds to 1970 midnight at UTC. The max value for a valid timestamp is this quantity right here. Any value greater than that isn't valid and would not be recognized. This corresponds to approximately the year 3000. I have no idea why we chose this specific number. It's something like April 25th, 2999, like 7 p.m. or something. I don't remember why this is. Anyway, in any case, valid dates are between 0 and this number, which provides us roughly 1,000 years of simulation time if you happen to need that. Not sure why we would, but there it is. There are also 2 other values that are used. One is never, and the value of never is 2 to the 63rd minus 1. And the other is invalid, which is 2 to the 64th minus 1. And those 2 values are used to flag when, for example, an object wants to say that it's reached steady state, it would return the value never. And if an object returns invalid, for example, it can't calculate the time, or there's some other error that requires the simulator to stop, then it would return this value instead. So these are the values that can be returned as a result of any of the event handlers that you would find in the update sequence. So the update sequence essentially starts each of these event handlers with a proposed time to advance the clock to. And so all the objects are required to advance the clock to T1, and then they are asked to propose a time for the next T1. And what this main loop does is then it uses the shortest T2 time for the update for the next T1. And so that sequence of moving the clock forward, making sure that all the devices, agents have updated accordingly to that time, and then asking them what the next time step, that is the main process. So let's go into some detail on how each of these works. So the pre-commit is essentially done once per time step before the synchronization loops begin. Pre-sync, sync, and post-sync are done over and over until the requested time is greater than the the proposed time is greater than the requested time. So we're asking a device to advance to T1, and as long as devices return a value of T2 greater than T1, we can get out of this loop. But if any device returns a value of T2 equal to T1, then this loop here, this innermost synchronization loop, will continue to process. So it will keep going until all the devices propose a value of T2 greater than T1, and that becomes the time that we commit moving forward to, the minimum value. So this is the main process, and what we'll do now is kind of go through each one of these individually to understand how they work. So first is the pre-commit. The idea behind a pre-commit is that we prepare all the objects for this synchronization innermost loop that we're going to run. So we do things like initializing accumulators, setting up any kind of iteration-based accumulator as well. So we may have accumulators that work on the outermost level, and we may have accumulators that work on the innermost level. We may have lists that we need to build, things like that. We also read any inputs from external sources, things that you would want to do only once per time step, and then you would never do again. So you would not need to read, for example, the inputs during the innermost sync loops, but you need to get those inputs in so that the values are up to date with the current timestamp. Any inputs that you need to update from other objects, you would also read at that point in time, unless they're part of the main synchronization loop. And of course, any updates to filters, schedules, and so on are also completed during this phase. Once that's all done, we can go into this innermost time synchronization loop. And what happens here is that the solver runs through each object, and it does them. When it's a pre-sync, it's done in a top-down order through the ranks. And we'll talk about the ranks in a little bit more detail. But every object has a rank, and the highest rank objects are processed first during pre-sync. And we process down through the ranks to the lowest rank object. Within a given rank, all the objects can be synchronized in parallel if there are threads available to do so. But if there aren't, and it doesn't matter if there aren't, it's just a speed issue. The objects will be synchronized sequentially in whatever order they happen to be defined in. There is no specific order since parallelism is allowed. It's not an issue. And as we process through these different ranks, of course, once you've completed one rank, then all the objects in the next rank can be processed, and then finally all the objects in the bottommost rank all the way down through. That process is reversed when we use synchronization. During synchronization, we synchronize from the bottom up. So from the lowest rank object up through the highest rank object. And we'll see in a minute why this is done. But if you think about dependencies, right? If I have an object that is dependent on information from a parent object, then that parent object would presumably have a higher rank, and I could then depend on that information being updated first on a top-down pass. And then I could update information in the parent on a bottom-up pass, and I could be guaranteed that the parent is processed afterwards, and so its information would be up to date during the bottom-up pass. And then the process is repeated again the same way with a pre-sync during the post-sync event from top down. And this allows us to construct all sorts of different solution mechanisms for different objects that relate to each other. And as we'll see with different solvers, each solver uses this structure differently. And that's how we get the entire system to coordinate the solutions to all the different objects. So it takes some getting used to understand how this works, but we'll see a very simple example in a few minutes that helps illustrate and perhaps build your understanding of how this works. And then finally, when all of this is done and every object has returned a timestamp that's greater than the requested time, then the processing is done, and we can then exit out and go to the commit process for that timestamp. And the commit process basically completes all the outer iteration, every one-time iteration information for each time step. So it'll close iteration-based accumulators and wrap up any information needed in one-time step accumulators, and write outputs to external sinks, CSV files and so on and so forth. And so this is basically the final step in a time step. And once that's done, then the entire update process is finished, and the main synchronization loop is done. And then we can consider advancing to the next time step if that's necessary. So let's look at a simple example. So let's suppose that we want to calculate the average of some input value. This average can be calculated either once per time step or once per iteration. So if we need to calculate the average once per time step, then we set up the accumulators during the pre-commit process, and during synchronization, we calculate the value that we get the input, and we add the input to the accumulator, and we add a counter. If you recall, the way you calculate an average is you sum up all the values and you divide by the number of values that you sampled. And then at the end of the time step, when we do the commit, we calculate the final answer, and then that's the answer that we use as the solution. Now, if instead we wanted to calculate the average over each iteration instead of over all iterations over a given time step, then we would do the same operations, but we would do them at the pre-sync stage, where we calculate the value x. In pre-sync, we would initialize the value x in the counter n. We would then get the input, based on that input, we would update the accumulator and update the counters, and then during the post-sync, in each iteration, we would calculate the complete answer, the final answer, and then we would post that as the solution. So you can see that depending on whether you need to do the operation once per time step or once per iteration, you would then use different event handlers to implement the solution. And so this is the basic idea. Of course, when we do this for a variety of objects, it can get quite a bit more complex, and the interactions between objects can get much more complex. And in fact, you will often find objects do both simultaneously. They will perform some operations at the level of iterations and some operations at the level of a time step. And generally, that's how we design the behavior of each object in Gridlab-D. So that's basically how the core itself works. There's really, other than that, I think what's important to understand is how the ranks work, because the ranks determine the order in which objects are updated. Ranks are basically set by the modules that are responsible for these. So a rank will determine the order and the parallelization that's possible. So you can think of it this way. Some objects must be updated sequentially, and other objects can be updated concurrently. And then, of course, somewhere in between are objects that can sort of, fit both categories. And what Gridlab-D's core solver does is sequence objects according to whether or not they must be sequential, and then parallelize objects according to whether they can be concurrent. And so that is the essential function of the solver, and it's the ranks that determine this. So because every module is required to determine the ranks for objects, that means that you really should not be setting the ranks yourself. So if an object is defined in a module class, you should leave the rank alone. You should not touch it. It is okay to manipulate the ranks of classes that you implement with your own runtime classes. So if you're defining your own class, you can actually set ranks in order to specify the order in which classes, objects get updated if they're members of that class. One really important caveat is that setting a parent has the effect of changing the rank such that the rank of the parent is greater than the object that set the parent. The idea is to force parents to be processed first on top-down iterations, such as pre-sync and post-sync, and have them be updated afterwards on bottom-up. Now, this won't interfere with how the ranks of are set by the solvers, because basically what's happening is that the promotion doesn't change the ordering overall on the top down and bottom up. It just would delay it a little bit. Yeah, there's a question here about how ranks are different from one module to another. So for example, if we are using a forward back sweep, and we'll talk about this a little bit later when we talk about the power flow solvers, but if you're using a forward back sweep solver, the ranks are what determines the sweeping order. So the swing bus, for example, would be the highest ranked object, and load buses would be the lowest ranked object. So the forward back sweep method sets all the ranks such that the sweeping algorithm works correctly within that particular solver method. However, if you're using a Newton-Raphson solver, the ranks are set differently. And I'm trying to remember, I don't recall whether nodes or links are higher or lower rank, but in any case, you only have two ranks for Newton-Raphson, one for nodes and one for links. And so you can see that according to the solver method, the ranking system would be completely different. And in fact, the Newton-Raphson solver gives you a very flat rank hierarchy, only too high, and a forward back sweep gives you a very deep one. Technically, the depth is the graph radius from essentially the graph distance from the swing bus to the most distant load on the network. So yes, the ranks will be quite different according to which solver you're using, which is potentially relevant to the performance of the solver. As it turns out, forward back sweep is generally a better performer for radial systems, but it doesn't work for network systems. Okay, so let's move on to thermal solvers. So the thermal solvers are used to solve buildings. So buildings are essentially large, well, depending on the size of the building, they're essentially large thermal masses that have HVAC systems that affect the air temperature. And of course, the air temperature is what we directly feel as occupants of the building, but the thermal mass of the building has a pretty significant impact on the overall behavior of the building over time. And of course, all the things happening in the building or happening to the building affect the heat gains and losses. And it's the interaction between the air temperature, the mass temperature, and these heat gains and losses that gives the buildings their rich dynamic behavior. And so in general, the way we define a building model is we have a sort of an outdoor node, which has the ambient weather conditions that the building is exposed to, and then one or more nodes inside the building. Generally, we have a minimum of two nodes, one for the mass and the other for the air. But for larger buildings, we may have more nodes than that. And then each of the nodes are connected with conductivity. So we have material, for example, the envelope of the building that separates the outdoor air from the indoor air. And then, of course, the surfaces of all the fixtures and the interior walls and the mass of the building itself separates the air from the mass of the building. And that, of course, affects the way in which the mass transfers heat back to the air or absorbs heat from the air. And so this is generally how buildings are constructed in Gridlab-D, but we have to solve them a little bit differently according to the type of building. So here's an example of the thermal network model for a single family home, where we have the outdoor air temperature, the UA for the envelope of the building, the indoor air temperature, its mass, its thermal mass, which is not very large, but still of some significance. And then the UA between the air and the mass of the building itself, the temperature of the mass of the building, and then its thermal mass, which is quite significant. It's the majority of the thermal mass of the building itself, definitely greater than 90% of the thermal mass. And then, of course, all the heat sources. So the HVAC system itself, which has a thermostat that's controlled from the air temperature. And then all the other internal gains, which come from all the end uses, your refrigerator, the appliances, your range, the building occupants themselves, your lights and plugs, all that stuff adds heat to the building when it's running. And then, of course, the sun, which adds heat to the building. And all these sources of heat put their heat either into the air or into the mass or some mix of the two. So each source of heat then can deliver its heat to either the air or the mass. And once we calculate all of this, we end up with these two differential equations, which is the rate of change of the internal air is some function of the air temperature and the mass temperature, and the rate of change of the mass is also some function of the air temperature and the mass temperature, plus these gains, the heat gains to the system. And so, it's fairly straightforward to then calculate what these parameters are based on the basic properties of the network. And then what Gridlab-D does is it updates these properties, UA, UM, CA, and Q mass, Q air, all of these as a function of time. And so as time goes by and our end use loads and our climate change, these parameters will change and the dynamics of the building will change, and the building's behavior will update. So this is the simplest building model. And the solution to this is essentially a second order differential equation. And the parameters of that are shown here. And then, of course, solving the second order differential equation really amounts to just solving a quadratic equation for these parameters. And so for those of you who remember your differential equations or know how to do this with the Laplace transform, it's a pretty straightforward solution. And so Gridlab-D implements that solution for every house in the model, and can therefore solve both time for state and state for time, as we've discussed previously. So that's the basic idea. And then, of course, all the details of how we update those values come from both the internal sources and the HVAC system, and of course, external sources. So internal sources are all the end uses, the occupants, and then the effective solar gains. I guess that should be listed as external sources, but the effective solar gains on the mass, right? Because the sun heats the mass, really, not the air, and then the mass radiates that heat into the air, conducts it into the air. And so the solar gains are treated. And of course, the HVAC system under the control of the thermostats will affect the heat gains and losses. And of course, you have some losses from devices themselves. So if you're running an appliance, for example, your stove or the oven, the heat from that eventually dissipates into the house itself, and it has to be added to the total gains. And then, of course, there's the weather effect on the conductivity of the envelope, through the envelope conductivity, and of course, any ventilation effects. So if there's wind or a stack effect in a building, that would also be accounted for in the ventilation effects. And all of this contributes to the heat gains and losses, which the HVAC system then has to deal with. Now, one of the key things in any simulation is appropriate sizing of the HVAC system itself. So what Gridlab-D does is when you provide it TMY data, it can then calculate the, it then has the minimum and maximum temperatures observed in the TMY data, and it can use that to size the equipment automatically for you. It does have an oversizing factor. Typically, I believe it's 50%. When it calculates the size of the equipment required, which it does basically by calculating the maximum heat load and the maximum cooling load, and whichever one is larger. If it's a heat pump, it uses that as the size of the heat pump. If it's not a heat pump, it just sizes the heating and cooling separately. But then it takes that result and it will increase it by some factor based on the oversizing factor. And then that determines the total capacity of the system itself. Generally, that gives you ample ability to do recovery and things like that when there's an outage, for example, and the house has to cool itself back down or heat itself back up. There are also other considerations in sizing. For example, the type of the system may be a factor, and you may want to change the oversize based on that. And of course, degradation. Older systems tend to not perform as well, and so they may not be able to handle conditions, particularly under climate change, where we see more extreme cooling requirements in systems that may be already 10 or 15 years old and not capable of handling that. So those are all things which we can implement in the models if we wish. But the default sizing system is pretty effective, so you don't really need to worry too much about this unless you're trying to model exceptional conditions in buildings. Another important aspect is building energy codes. So the way this is handled is with what's called the thermal integrity level. Your typical building is going to have a normal thermal integrity, which is going to be an older building that has been retrofitted or upgraded. So you can see here, this middle row here, row 3, is sort of your typical building. If you've got buildings that are sort of below par, then you can use below normal, little or very little, just to represent varying degrees of building performance degradation, leaky windows, poor insulation, and so on. If you've got a building that's above par, then you may have buildings that have extra insulation or say heat absorbing glass. These are things that would significantly improve the performance of the building over time. So setting the building integrity level basically is how you choose essentially what quality of construction is involved in a particular study. So it's a good idea to look at that. I believe normal is the default, if I'm not mistaken. And so it's not a bad idea to set that appropriately, because it can have a pretty significant impact on the overall performance of the buildings. Another important element of the model, we've talked about implicit end uses, and they use load shapes to drive the behavior of the end use. One thing that is commonly modeled explicitly is the water heater itself. If you're studying water heater retrofits, for example, or water heater demand response, you'll need to use the explicit water heater model, which has its own solver. The technique used here is to model the height of the thermocline. So this is the boundary layer between the cold water at the bottom of the tank and the hot water at the top of the tank. Water heaters do not mix water when they bring water in to replace hot water that's been removed. The water is added to the bottom in a laminar flow so that the mixing is minimized, and then that cold water slug is heated up. This is done so that your hot water remains hot as long as possible as you draw water out. If it were fully mixed, your hot water would start cooling off right away, and that would not be as comfortable. You'd find your water temperature varying quite quickly. There are also, most water heaters have 2 coils in them, and the upper coil is used when the boundary layer passes the halfway point. And the idea is that then you heat only the upper slug of water, and that doubles the reheat rate for someone using hot water. And so it helps make the water tank look more responsive. There is, over time, slow losses in mixing of the temperature, but it's quite slow, and it's because of heat transfer between the 2 layers and through the shell of the tank. And then, of course, there are heat losses, and those losses just, for cooling, it's quite slow, but those losses give rise to the standby load that you typically see on a water heater if you just let it sit without any demand. So what drives the water heater model is then the water consumption, and that is essentially driven from the same load shape as the water heater demand. So it's possible to simply take the demand load shape and use it to convert, the water heater load shape and use it to convert it to water demand on the water heater itself. And you get the same results. So that's a fairly typical way of modeling water heaters. And this is how the water heater model works. Another important aspect of the residential model is the circuit breaker, the panel model. Every end use in a house is assigned its own breaker. This has the advantage of doing two things. One is it limits the total power that can be consumed by any end use. And it helps mitigate solver problems when you have end uses that consume ridiculously large amounts of power. Because if you put too much load on the network solver itself will fail, unable to converge. So by having breakers open circuits that have excessive loads, that helps mitigate that to some extent. The other thing it allows us to do is study the effect of adding new end uses on breaker panels that have main breaker current limits that are insufficient. So for example, if we have houses that have 100 amp service and really just supply things like lights, plugs, refrigerators, and small loads, and then all of the other loads like a dryer and the water heater and the range are all gas loads, then when we convert those gas loads to electric loads, that main breaker may not be sufficient, and we would start seeing main breaker trips in the model. And that kind of situation would be an indication that the breaker panels need to be upgraded. So in doing an electrification study, it would be possible to identify how many breakers and how often they would trip as a result of electrification. And then we could deduce then how many homes would have to go through main panel upgrades. So this is a useful component of Gridlab-D's home model. All right, so moving on to larger buildings, the apartment building model is still undergoing development and validation, but I wanted to go through it to give you an idea of what the 4-zone model looks like and how it's developed. It's quite different from the residential model. It models multi-floor apartment buildings with both occupied and unoccupied units, as well as circulation spaces. And as you might imagine, in an apartment building, these three types of spaces are conditioned differently and controlled differently. And as a result, we do need to model them separately. And then, of course, we need to model the building mass once again, because that mass has an effect on the behavior of each space individually. Now, one thing about apartment buildings is that the circulation space can be loaded with apartment units in different ways. So you might have an apartment building with both sides of a hallway with units on it, or you might have an apartment building with only one side of the hallway with units on it, and then the other side is either a wall, exterior wall, or it might even be open to the outdoor. The other thing that we have is that the units, unoccupied and occupied units, may be randomly arranged. We don't know necessarily, how many units are unoccupied or which ones specifically are unoccupied. So the model does what's called diversified loading. And so it uses the fraction of occupied units, the fraction of unoccupied units to calculate the lumped parameter model. It does not attempt to model the individual units. That's kind of overkill for what Gridlab-D really needs. And then the last thing to consider is that the circulation space may be conditioned or it may be unconditioned. So if it's an indoor circulation, It might have its own HVAC and ventilation, or it might not. So that is also a consideration. And then finally, the heating and cooling systems may be entirely inside the units. They may be entirely central, or they may be some mixture of the two. And so the apartment building model will handle all of those possible arrangements. For the curious, this is the solution method for the apartment building. It's essentially a differential equation, four first-order differential equations that describe the relationship between the temperatures of apartment units that are occupied, unoccupied apartment units, the circulation, and then the mass. And so these are the basic equations. Now, each of these properties, the UAs and the masses, are calculated from the configuration information about the apartment building. And I'm not going to go into details of this, but it's essentially things like, how wide or how tall is the apartment building? How many floors does it have? How wide is the hallway? How many units are on each hallway? Things like that. By giving these dimensions to various aggregate properties of the apartment building, we can calculate all these UAs and CAs and so on. And then once we've calculated all of those and we've sized the equipment appropriately, we know what the equipment's behavior is going to be. So what the solver does is it goes through and determines the mode of the system given the conditions present in each of the lumped zones, so the occupied, unoccupied, and circulation. And then given those modes, it determines the equilibrium temperatures and then calculates the equilibrium load. That's the load needed to maintain steady state. So it doesn't calculate individual HVAC status, on or off status, but what it calculates instead is the diversified status. So what's the duty cycle of those units? And then it uses that essentially fractional load to calculate the final temperatures given the constraints. So if there are heat constraints on the capacity of the system, that might reduce the amount of heat gain or loss delivered by the HVAC system, and that would then reduce the effectiveness of the HVAC system in maintaining temperature, and we might see temperature deviations outside the desired set points for each of the zones. So this mechanism is a little bit different from individual homes, where you see the HVAC units turning on and off in discrete steps. In an apartment building, what you see is sort of the continuous aggregate load of all the HVAC units behaving separately, but added up as a diversified single load. So this gives us a very efficient model for larger buildings where modeling individual units would not be very efficient. Okay, so the way this works then is at the top level, what an apartment building does is it knows its total capacity. It's got a bit of an over-design factor to account for system degradation and failure in components and so on. And then it calculates the total power demand for all the occupied units, for all the circulation units, areas, and all the diversified loads. There are actually loads possible in unoccupied units because the temperature settings in unoccupied units are still there. They're just set to very far away from a comfortable set point, just to cover things like preventing pipe freezing and such. But usually the unoccupied units are very low. And then of course the diversified HVAC. One important note is that there's no panel or circuit breaker model in apartment buildings, given that that would probably be performance prohibitive. And the way the model works, we don't worry as much about individual end use overloads. That's not something that we would typically expect to see. So there isn't this panel breaker model that you find in the residential buildings. We have a question here. Does the thermal model assume that a single R or single U value for the thermal envelope can be adjusted based on other factors? Yes, so in the in both models, the window wall ratio is incorporated in calculating the envelope U value. And doors are also included, and roof and ground interfaces are also included in those calculations. And you can set each of those individually, and then when the house is initialized, the U values are calculated based on what you set those values to. So each house can actually be different, and you can create quite specific house models if you want to. You can even orient the house so that the solar exposure to the through the windows is accounted for, and you get diversity of solar exposures for each house. Any other questions on this, on the building modeling? All right, so I'm just going to talk briefly about commercial buildings before we move on to the power flow solvers. The commercial building models are not as developed as the residential building models. For small commercial buildings, we essentially use the same model as a house, but we have a rooftop package unit instead of heat pumps and sort of the diversity that you find in residential buildings. But otherwise, it's essentially the same. For large commercial, we don't have a thermal model yet for large commercial buildings. We plan to do something similar to apartment buildings, but for now, I would just recommend using the CUS data models. The CUS data that's provided, there's a model for doing that in Gridlab-D, and it gives you, commercial building loads, but unfortunately, you won't be able to implement demand response strategies with CUS unless you add those load sensitivities to the model itself. One thing, though, is we did add commercial parking structures. And the reason for this is because we need to be able to model EV charging infrastructure on commercial buildings. So obviously, commercial parking includes lighting and ventilation potentially, and you can have nighttime only lighting, or if it's underground parking, 24/7 lighting. But for EV charging infrastructure, what we've done is we've provided the total installed capacity of the EV charging infrastructure. So how many chargers do you have? How many of them are active? And then you can drive them with either schedules or players. Eventually, we hope to even model EVs individually and things like that. But at this point, it's pretty typical just to use a schedule or a player to model the EV charging load in commercial buildings. So that's it. What we can do now is take a 5-minute break. We will come back at 10:05 and resume, and we will talk about the power flow solvers, and that will be a wrap for this session.